Hi everyone, this is the video lesson for 5.3 optimization problems involving exponential functions, part 3. So before you continue watching, if you haven't watched part 1, which we talked about the warm-up and example 1, and if you haven't watched part 2, which we did some of example number 2, make sure you go back to that before continuing with part 3. So let's continue. In the last video, we stopped after doing number 3a, 3b, and 3c. In the last two parts, in part D, they're asking you to draw the graph the function. Now again, you want to go back and look at all the points that we have calculated and set up a proper scale. So again, on the independent axis, that's going to be time, which is measured in terms of, let's go back to the problem in terms of weeks. On the dependent axis, that's going to be population P of t, and that is in terms of hundreds. Now again, if you go back to the idea of curve sketching, there's a couple of things you want to think about. So for example, there's a horizontal asymptote, which we talked about in part B. So as t is approaching to infinity, over time what happens? Well, it's going to approach to 2,000 squirrels, or mathematically it's only 20. So when I set up the scale, when it go up by 5, so 5, 10, 15, and 20, and this will help you start with the first part of this diagram. So there's this horizontal asymptote at P of t equal to 20. And if you look at the independent axis, we found from the previous part the point of inflection occurs at 55 approximately. 55. So you can even set up a scale. Let's say we look at this in terms of 50. So 50, 100, and 150. So roughly speaking, something like that. 50, 100, 150. Now again, we're going to combine all the information that we've calculated so far. So one idea was the point of inflection is 54.9 and 10. So it's going to be roughly right there. You can label this as the inflection point, or the point of inflection, 54.9 and 10. And from part A, we talked about the initial population, which was 5, which really means 500. But there it is. You can even label this. That's going to be 0 and 5. Now, without doing all the increasing, decreasing concavity like we did with the previous topic, curve sketching, you can tell it's going to look roughly something like this. And again, think about this last part. The population's approaching to 20, or really 2,000 squirrels. Now, that's the graph for part D. In part E, they're asking you to explain the meaning of the point of inflection in terms of squirrel population growth. So this has to do with concavity. And since it's a word problem, we can talk about the meaning. Let's extract that from the math. So what happens is, if you look at the first 54.9 weeks, the population is increasing. So the first thing you can write down is population increases up to 54.5 or 54.9, or you can even just say 55. Then after the point of inflection, what you notice is it's concaving down. So again, it went concave up, hits the inflection point, then it's concave down. So the second concept is it starts slowing down, slows down. And what happens? As it's slowing down, it's going to approach over time the 20. So it slows down to a population of 20 over time. So again, if you look at the curve, first it's concave up, which is its first part, it's increasing. It continues to increase, however, it's now concave down, which means it's slowing down over time. And it eventually will approach to P equal to 20. One more example. Example number 3, number 11 on page 246. The question says, for f of x equal to x squared times e to the x, determine the intervals of increase and decrease. And in part B, determine the absolute minimum value of f of x. So again, press pause, try this for 5 minutes, so that way we know where you are in terms of your math skills. And when you press play again, I'll be right here. Here we go. So, to find the interval of increase and decrease, first you have to find inflection points. And you're finding, not inflection points, to find critical points. That was my mistake. I'll say it again. To find the intervals of increase and decrease, you must first find critical points. And to find critical points, you have to find the first derivative and set it to 0. So again, by inspection, f of x is going to be x squared times e to the x, which means you're going to apply the product rule. You differentiate the first, that's going to be 2x. You copy the second, plus. You copy the first, and you multiply by the derivative of the second term, and again, the derivative of e to the x is still going to be e to the x. You're now going to set this to 0. You go to solve for x. Notice there's a common factor of x and e to the x, which you can bring to the front. And in the bracket, it's going to be 2 plus x. Now, again, you can divide this into 3 different columns, and you can solve for x respectively. In the first case, x is going to be 0. In the second case, and again, we did this for the third time in this lesson, e to the x is going to be 0. This implies there's no solution, and that's perfectly okay. In the last column, 2 plus x is going to be 0, which means x is going to be negative 2. Again, form the habit of finding the location. Don't just write down the x value for critical points. Write down the actual location. So again, you can plug it back in to the original function. And when you plug in x to be 0, the corresponding y value is also going to be 0. And again, all you're doing is you're taking 0 to the power of 2 times e to the power of 0. Likewise, if you plug in negative 2, that's going to give you negative 2 quantity squared times e to the power of negative 2. And if you round this, it's going to be approximately 0.5. Now, once you find the critical points, you're now ready to find the interval of increase and decrease. Again, you draw a number line, you set up the 2 anchors. Always put this in ascending order, so negative 2 and 0. Again, you can pick a number less than negative 2, pick another number in between negative 2 and 0, pick a third number that's positive, and what happens is, if you pick, let's say, negative 3, and you plug it back to here, right? That's going to be f prime. This will give you negative times positive times negative, which ultimately is going to be positive, which means it's going to be increasing. Likewise, let's say you pick negative 1, you plug it back in, that's going to give you negative times positive times positive. When you multiply them, that's going to be negative, which means it'll be decreasing. Last but not least, if you plug in the number 1, that's going to give you positive, 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 which is increasing. So again, therefore, the interval of increase is when x is less than negative 2, or when it's greater than 0. Therefore, the interval of decrease occurs when x is in between negative 2 and 0. So that's part A. Now in part B, they're asking you to determine the absolute minimum value of f of x. And again, you can go through the first derivative test, which is what I'm going to show you in a moment. Ideally, you could find f double prime, plug it back in. That's also known as the second derivative test. And again, you don't really need that in this case. So you go back and you look at the intervals of increase and decrease, and here's what you should notice. The function is increasing, then it's decreasing. So this number is going to be the maximum. And again, you want to form the location. So the maximum is going to be at -2 and 0.5. Now likewise, if you look at the second part, notice the function is decreasing, then it's increasing. That's also known as a minimum. And again, I'm using the first derivative test, and this is located at 0, 0. Now, the question is asking for the absolute minimum. And if you graph this and you go through the whole algorithm, you would discover that the absolute minimum is going to be 0, 0. Now, they didn't ask for the maximum, I know, but if you really go through the whole process, it turns out to be a local maximum at -2 and 0.5, and an absolute minimum at 0, 0. So that is example number 3. And again, really important, you go back and you try number 1 of 16 on page 245. Practice again and again. And then when you're tired, you practice a little bit more. And this is how you become stronger and make some improvements over time. I hope this makes sense.